Okay, welcome everybody to this plenary talk. It's my great pleasure to introduce Alessandro Gabbana. Alessandro actually comes from the PhD program where I was involved myself a few years back, HPC LEAP, and he did very important and very nice work regarding a relativistic lattice-Boltzmann method in collaboration with a group in Ferrara. He will tell us about theory and applications behind these very important modern development of lattice-Boltzmann methods. So Alessandro, you have 40 minutes in total, 30 plus 10 of questions. When you reach 30 minutes, I give you a sign, okay?
Okay, thank you.
The floor is yours. Please go ahead.
Thank you, Mauro, for the introduction. And let me start by thanking all the organizing committee for making still possible to have this conference, and of course for the invitation as well. So in today's talk, I will give you a brief overview of the methodological development in the field of relativistic extension of the lattice-Boltzmann method, and I will also give you some details on potential application. I will not give you too many details on the mathematical foundation of the method, but if you're interested in that, we have recently published an extensive review where you can find all these mathematical details. To start, I will mention where these kind of solvers find application. And let me start by saying that it's actually not exaggerated to say that we are right now living a golden age for relativistic hydrodynamics. The reason for that is that alongside traditional fields of application, such as astrophysics and cosmology, in the past decades, new areas of physics have gained, like relativistic hydrodynamics, have gained a lot of attention in other fields of physics, such as, for example, high energy physics, as well as condensed matter physics, in particular in connection with the study of the quark-gluon plasma and of the electronic transport in graphene. Arguably, the quark-gluon plasma has been the real driver in this surge of interest, and that is mostly thanks to the very huge amount of experimental results coming from the RHIC and the LHC particle accelerator, which range from the first observation of the quark-gluon plasma to the more recent exciting observation of the smallest droplet ever made in a lab, which basically consists of a fireball of quark-gluon plasma of the size of just a couple of protons in size. Nevertheless, the definition of the theory of relativistic dissipative hydrodynamics comes with several problems, and that was noticed already in the early days when it was observed that naive covariant formulation of the Navier-Stokes leads to superluminal propagation, which is clearly unphysical, and in turn to unstable numerical behavior. Many attempts have been made to restore causality in the Navier-Stokes equation. The work of Israel and Stewart back in the 70s has served for a long time as the reference frame for several decades. And then you can see that there is some strong correlation between the development in dissipative hydrodynamics and the experimental results from quark-gluon plasma, since it has been observed that this Israel-Stewart formulation was not sufficient to reproduce accurately some of the experimental results, in particular there was poor agreement with some kinetic theory result, and therefore many other groups in the past 2 decades have tried to formulate new framework to develop a consistent formulation for the relativistic macroscopic equation for a dissipative fluid. It is probably fair to say that this is still, in some sense, an open problem, and there is still a lot of ongoing research on this side. For this reason, it is often preferable to follow a kinetic approach, and which is obviously free of the trouble coming from the relativistic Navier-Stokes equation. And in this framework, it seems almost natural, at least desirable, to have like a lattice Boltzmann scheme, where by construction the particle travel at a finite speed at a given time step, hopping from one point of the grid to another one, and thus restoring causality by construction. And furthermore, like dissipative effects, which are connected with this causal and unstable behavior, emerge naturally from the kinetic layer in the trends towards the local equilibrium. And in this sense, like there is like a computational efficiency is just a nice feature, but in this relativistic lattice Boltzmann method, which, as I mentioned, has many more even conceptual motivation for being developed. I think it's beneficial at this time to introduce the covariant version of the Boltzmann equation, where, as customary in the lattice Boltzmann framework, we will work in a relaxation time approximation, and therefore we replace the collisional operator with a simplified single time relaxation model given by the Anderson-Witting collisional operator, which describes the evolution of the system as a trend towards a local equilibrium, which in the relativistic regime is given by the Maxwell-Jüttner distribution, which is the relativistic extension of the Maxwell-Boltzmann distribution. One key difference is that, as you can see here, like the particle's energy is linked, the connection between the particle energy and momentum is not quadratic as in the classic case. The expression, you see, is more complicated. It's slightly simpler when we consider massless particle, but this is basically at the root of all the complexity that one encounters in the development of this type of scheme. I was checking while preparing this slide, and I noticed that it's actually the birthday of the relativistic lattice Boltzmann method, since in July 2010, you see, this is the cover of Physical Review letter, and this is the first paper published where the group at ETH with Miller Mendoza and Professor Herman, together with Bruce Bogosian and Sauro Suchi, developed the first version of this relativistic extension of the lattice Boltzmann method. The first methods that have been developed, like they were following a top-down approach. The reason for that is that, as I mentioned, like the Jüttner distribution comes with certain complication, and in particular, it's not trivial to expand it in a Hermite set of polynomials like we do with the Boltzmann distribution, and not having this extension in their hand. What they did was to follow up this top-down approach, where they were matching the moments of the distribution with a double distribution approach, where you choose, say, toy, let me say, distribution function, where develop to separately describe the evolution of the conservation equation for the particle number and for the energy momentum. One nice feature of this method was that it was possible to use like standard lattices, as you can see here. But the major drawback was that it was becoming quickly unstable as long as we were working in with Lorentz factors, flows with Lorentz factors, even just above 1. So to cure this problem, it was then later taken into consideration a bottom-up approach instead, where the relativistic lattice-Boltzmann method was developed starting from the kinetic layer, and the coupling with a Gauss-type quadrature. Initially, the method was working off lattice on spherical with spherical design quadratures. The reason for that is that the first methods were mainly restricted to the case of massless particles, so to the so-called ultra-relativistic regime. So although, like, of course, we lose here some nice properties such as perfect streaming, we have the advantage that this method was actually stable for flows with Lorentz factors up to 1.4, 1.5, and was comparing very well with other benchmarks, benchmark codes from the literature. Naturally, the question that follows is, can we play the same game and stay on the lattice? The answer is yes, although, of course, it's not as easy as one would like. So to put it very short, like compared to the classic lattice-Boltzmann method, let's say Lorentz invariance, it's much more costly than Galilean invariance, and the result is that you need lattices with a very large amount of discrete velocity. Here I show you two examples. On the left-hand side, the method developed for the specific to the ultra-relativistic case, where you see the discrete velocity are found to live on the intersection between a Cartesian grid and a sphere. The reason for that is that we have massless particles that all traveling at the speed of light, and so they have to lie on the sphere. And on the right-hand side, we have this other method where instead we consider massive particles. This gives us the freedom to take more wide range of discrete velocities. Let me just go briefly through how this kind of quadrature-based models are developed. So the starting point is polynomial expansion of the equilibrium distribution in a suitable set of polynomials, which in the best case, they should have the properties that their projection coefficient coincide with the moment of the distribution function. And you might recognize these properties in the connection between the Hermite polynomials and the Maxwell-Boltzmann distribution in the classical case. These polynomials in the relativistic case are not known, but that's not a problem. We can build them on our own with a standard Gram-Schmidt procedure imposing this kind of condition. Once this is done, then the next stage is to then develop Gauss-type quadrature up to a certain order n, which ensures the exact preservation of all the moments of the distribution to order n. And after that, then one simply need to derive the discrete relativistic Boltzmann equation and basically implement and it's ready to implement the method. Clearly, the most important part in this derivation, more complicated one also, is the derivation of the quadrature rule. So let me show you how this could be done, for example. So one way to go is to apply the so-called quadrature we prescribed abscissa formulated by Filippi and colleagues, in which one requires the preservation of the orthonormal condition in the continuum as much in the discrete. And basically, what one does is to plug like a set of discrete velocity in this equation, and then try to find a solution for the weights in such a way that all the weights are strictly positive. So for the relativistic case, one can discretize the momentum quadrivectors in this form, where we have a free parameter that I call V0, which basically ensures that information doesn't, it can be chosen arbitrarily in principle, but should be such that the information doesn't propagate faster than the speed of light. In the ultra-relativistic limit, we have some extra like tricks to simplify the work when we want to define this on-lattice type quadrature. So first of all, we know where to look for. So we know, again, we have to look for velocity vectors that are living at the intersection with a sphere in 3D, and here with a circle in 2 dimensions. And we basically, what we do is we increase this radius in order to have more and more velocities and stop whenever we have enough to find a solution. This procedure, in principle, will lead to discrete vectors with a very, very long radius. But we can exploit the fact that here, in this parameterization, we have that for massless particle, the time component of the discrete of the momentum vector, which is the energy of the particle, it's here not well defined, and we exploit this by adding extra degree of freedom in such a way that we velocity set with several energy shells, and which are overlapped with the same velocities, and that help us to find the quadrature in an easier way. You can see this procedure as the result of a product rule, where like Gauss-Leger quadrature is applied for the radial part, and then some other type of quadrature is then applied to discretize the angular part. When we deal with massive particles, as I said, we have more freedom in how to choose the vectors, but then we don't know where to look for. So in principle, this is a huge combinatorial problem. And what one does is first, select enough symmetry groups such to make the system of equation that needs to be solved determined, and then look for a solution of the weight that needs to be all positive. And in this sketch, you can see how one of these system looks like. So we have that all the weights can be seen as function of this parameter V0, and then here we have a very short range of where all the weights are positive. So what one does is, in principle, scan through a lot of different possible stencil combination and look for this type of solution for different values of the fluid's rest mass. And the result of this is that we have basically developed like a tool which is in principle able to cover a very wide range of parameters, going all the way from the ultra-relativistic regime to mild relativistic regime down to basically classic fluids. One more important thing in the development of the method is the control of the transport coefficient. And in the classic case, we are used to basically perform some asymptotic expansion and connect the kinetic layer to the macroscopic one. You can do the same in the relativistic framework, but then there is this interesting fact that the Chapman-Enskog expansion and Grad method of moment gives slightly different expression for the transport coefficient. So to give an example, for the shear viscosity, both methods predict a linear dependence with the pressure and the relaxation time, but then they differ by a coefficient, which, as you can see here, tends to the same result in the classic case, as we well know, and then we have major differences in the ultra-relativistic case. This discrepancy has been object of several works in the past decade, and all of this converging to the fact that the Chapman-Enskog expansion should be the preferred route to connect the kinetic layer to the macroscopic one, in particular the group of Denikol, extended the Grad method of moment using a different expansion basis, and showing that as you include more and more moments in the expansion, you eventually converge with to the Grad method of moment, to the Chapman-Enskog result. But naturally, that doesn't necessarily mean that our method follows those results. So we need to be sure of that, and to make sure of that, what we did was basically to calibrate our method, de facto measuring the transport coefficient from numerical simulation. So we set up a numerical simulation where we can have some analytic or semi-analytic solution that depends on one of the transport coefficient of interest, and then we try to fit this expression from the result of the simulation. And as we can see in this figure, our results clearly connect our method to the results of the Chapman-Enskog expansion. We did the same work for all the other transport coefficients, extending also in 2D. The reason for doing that is that we are interested in studying the electronic transport in graphene, and as we know, this is de facto a 2D-dimensional material. Okay, so let's go back now to the application and see where this type of models can find application. So we start from quark-gluon plasma, for which here we have a sketch of the collision between heavy ion nuclei, which are typically performed inside particle acceleration, and where the aim is to recreate the extreme state of matter with extreme high values of density and temperature, which was possibly could have been observed in the first microseconds after that Big Bang, and possibly also inside the core of neutron stars, but about that maybe we will hear something more after lunch. So you see, in the first instances, after the collision, what one observes is a strong anisotropy, which can be measured in experiments, and which are found to depend strongly on the specific equation of state and on other transport properties such as the shear and bulk viscosity. A full relativistic lattice-Boltzmann-based implementation of this setup still lacking. Here I can only show you a few snapshots of simulation where we qualitatively reproduce this setup, but more quantitative analysis of this type of simulation will need to be object of future works. On the other hand, extensive work has been done for what concerns like the study of shock waves. In fact, this is a typical way to benchmark and validate the model. And what one does is to compare against other solvers available in the literature. So I assume you are all very familiar with this type of benchmark. So basically here we have a tube filled with a gas divided into chambers divided by a thin membrane. The gas in the two different chambers are like take different values for temperature, initial temperature and initial density. And once you remove this membrane, then shock and rarefaction waves develop. In this simulation, we keep fixed the ratio between the shear viscosity and the entropy density, and following the same expression used by other solvers in the study of quark-gluon plasma. Here I show you a comparison at this ratio eta over s 0.1, which is typical value for the quark-gluon plasma, in which we compare against Monte Carlo approach, Monte Carlo solver for the full Boltzmann equation, this also method called BUMPS, and we show like an excellent agreement in the macroscopic field. Obviously, BUMPS can then provide much more interesting information about the particle distribution function, while in the lattice Boltzmann you can only calculate macroscopic quantities and components of the tensors, like the energy momentum tensors. But the big advantage is that to produce this simulation, it takes just a couple of seconds on my laptop, while it takes an order of 1 day in a supercomputer in Frankfurt. At least these were the figures that were reported to me a couple of years ago. So in this first case, I was showing you the ultra-relativistic case, and here I show you what happens when we introduce fluids with relevant value of the particles rest mass. Here in this comparison, we compare again yet another solver developed by the group in Catania, which solves again the full Boltzmann equation with a so-called test particle methods. Besides an excellent agreement in the macroscopic fields, we have also a decent good agreement in other derived quantities, such as the heat flux, the non-equilibrium part of the energy momentum tensor, and we also see in the in the lower right panel the dynamic pressure, which is related to the effect coming from the bulk viscosity. In all this comparison, we basically have very good agreement, except for the exact point where the wavefront devolves, where obviously you have still a very strong discontinuity, so it's not obvious that one or the other method is doing exactly the correct job there.
Alessandro, you have 10 minutes, eh?
Okay, thanks. Let me quickly show you that there are also a couple of analytic solutions for this type of problem. For the specific case where you have an envisaged fluid, we cannot work with zero viscosity, of course, but we can approximate that much better as long as you use very large grids, and you see that we get very good results. I would also like to show you where instead we start hitting problems, and that's where we move away from the hydrodynamic regime and we move towards basically here in the transition, in a transition regime, where still qualitatively we still recover decently well the behavior of the solution, while we really fail when we move to the ballistic regime. It has been shown then by other people, by Victor Ambrus and Robert Blaga at the University of Timisoara, in a very nice paper, that you can actually still extend the method to handle this ballistic regime and to study, for example, rarefied gases by using very high order quadratures. Okay, let me then go to the next application very quickly, which is the transport of the electronic transport in graphene, which is motivated by the fact that these they exhibit a hydrodynamic behavior due to the fact that electron-electron collision are dominant over the interaction between electrons and phonons already at room temperature. And the use of this relativistic method is justified by the fact that the relativistic dispersion is, say, pseudo-relativistic one, in which the Fermi velocity takes the place of the speed of light. Actually, a lot of methodological development have specified these two-dimensional cases, and have investigated the possibility to observe different type of instabilities like Rayleigh-Benard, Kelvin-Helmont, as well more in general as the possibility of triggering and observing turbulent signals in this type of condensed matter system. So in these works, it was suggested that actually it was not too far away the possibility of observing this kind of turbulent signals already, say 10 years ago, with the parameter range of typical experiments of 10 years ago. But yet, as we are speaking today, this type of things has not been observed. And the reason for that is that in this kind of simulation, were, say, a bit overly idealized, and they were not taking into account the interaction with, say, impurities and phonons, which tend to have like a destructive effect on the onset of turbulence. Once you introduce in the model this type of effects, and I will go, sorry, a bit quickly here because I want to show you something more as well. Once you introduce this type of interaction with phonons and impurities and set like standard choose physical values comparable with those at which experiment take place, and what you end up is basically just laminar flows. Of course, what we can do, and what in experiments, real experiments, they cannot, is play with the parameters. So we can tune this time, the typical interaction time with phonons and impurities, and increasing that, then we then can identify the onset of say, pre-turbulent signals. Then you can parameterize this, and then you can perform several simulations, go identify where this crossover from laminar to turbulent regimes take place. And we have parameterized this extending using an extended version of the Reynolds number definition, in which we make use of effective viscosity, which is, say, incremented by the effect of the interaction with phonons. And the end of the story is that basically we are still quite far away from the possibility of observing these kind of signals in real experiments, because like the parameter regimes that can be explored now are, say, a factor 10 of what we see in this figure. Let me conclude this talk with a third possible application, which we have developed just basically just in time for this talk. We submitted this paper last Saturday, and it's an attempt to apply the lattice-Boltzmann method to study the radiative transport in astrophysics. This, strictly speaking, is not exactly a relativistic lattice-Boltzmann method, but we made use of the lesson learned during the methodological development of the relativistic lattice-Boltzmann method and apply to this situation, where we study the interaction between the radiation and fluid, which can interact by emission, absorption, and scattering. And let me mention, like, we are obviously interested in studying a very wide range of parameter regimes, in principle spanning all the way from optical thin to optically thick regimes. And for doing that, as we've seen in a couple of slides before, we need very high order quadrature to handle this kind of ballistic regimes. And the first results that we're getting are quite promising. So let me spend just 2 minutes on this, and then I promise I'll wrap it up. So what we have here is a simulation of relativistic jet at with Lorentz factor about 7 or 10. And in the first panel, you see what you get conducting a purely hydrodynamic simulation in the absence of dissipative effect, so say hydrodynamics. And then in the other 2 panels, we have a coupling of this hydrocode with radiative transport. In the lower panel, we have the coupling with this M1 say approach. What is M1? M1 is like a moment-based approach, in which this is basically state-of-the-art for radiative transport in astrophysics. And what you do is you evolve separately the first n moments of the distribution, and for which you need n+1 equations. So obviously you need a closure or at the order n+1, which in general is not necessarily known, and even more in general, there are many of them, and some work better, some work less better. In this M1 code, one of the most well-known pitfalls of this method is that, and we've seen this morning in the talk by Daniele Simeoni, that when some two radiative beam cross, they actually instead they actually interact between themselves, and then follow a direction that is not the correct one. And we see that we have already qualitatively very different results in the comparing the result provided by this M1 code and our lattice-Boltzmann based approach. So in the M1 code, the jet actually moves faster than the purely hydro code, and this sounds a bit counterintuitive, because basically you are giving some, the fluid is giving some energy to produce radiation, and should not move faster than when radiation is absent. And we are obviously it's difficult to say like our simulation is correct and M1 is wrong. In principle, can be that even both cases are wrong. But what makes us very confident that our case is at least more reasonable than the M1 code is that when we look at the radiation energy spectrum here, profile, in which we can see that basically here we are at the level where we inject near the injection of the energy from the bottom, and you see this triangle at the lower in this lower area of this panel. I don't know if you see my mouse moving, but anyway. So in this right-hand side, we have this M1 code, and we see that there is this crossing and there is this accumulation of energy along the axis of propagation. And that is the reason why basically you see here this jet moves faster, and also the front is more narrow compared to the lattice Boltzmann one. So we consider this a very good start for this new method. Obviously, a lot of development will be required in the near future. There's also room for a lot of possible application, and I'm quite confident that in the next year in Viterbo, hopefully, we will be able to be there all together, and we will probably be able to hear a bit more about the development along these lines. So to conclude, I gave you an overview of many years of development of this lattice Boltzmann method extended to tackle relativistic regimes. There's a lot of different type of methods. Some works better in some regime, some in others, depending on what the application, in which type of application you're interested. In principle, we are able to preserve the computational advantages of classical lattice Boltzmann method, and I've shown you a couple of possible field of application. I have to be fair and say that so far in the past 10 years, it's been mostly about methodological development. So the actual application is still lacking. Like people really using this method are very rare. I would say it's only us. And that's why it's important to reach out to these communities and to see if our method can give like a significant contribute, like it looks like to be for this astrophysical application that I've shown you. I conclude thanking you all for your attention, and of course thanking all the people that have worked with me in the past years, from Sauro to Lele, also known as Professor Tripiccione, Daniele, and then the people for different groups like Francesco Pellegrini and Marco Polini that has worked with us in the field of graphene, in the analysis of pre-turbulent regime in graphene, Salvatore Plumari and Vincenzo Greco, which have collaborated with us in the study of shock waves in quark-gluon plasma, and lately, last but not least, Lucas Vai and Luciano Rezzolla, with who we have recently, as you've seen, started collaborating in this application to astrophysics. Thank you again, and obviously ready to take any questions.
Thank you very much, Alessandro, for this inspiring overview lecture. So we have time for questions from the audience.
Can I ask a question?
Yeah, sure.
Well,
I can't hear well. I can't hear well.
Now?
Yeah, now it's a bit better.
Okay. Well, Okay, anyway, so if you hear me, I want to ask actually maybe a provocative question. Well, I was a little bit involved in that business with Miller and Sauer some time ago, not very long, but I see the progress. Very nice. But my question is this. So you call it lattice Boltzmann and you're looking into the high energy kind of physics all the time. But on the other hand, we have non-relativistic lattice Boltzmann seemingly well established, right? So what about whether any of these models have a natural limit in what we know of kind of our low order lattices? Do they how do you match to that limit, or if you match to that limit?
Okay, so there are two possible ways to answer this question. Well, first, like from a purely mathematical point of view, let me find the right. So here, like, if we take the limit for this type of...
I remember this picture.
If we take this limit for like when the rest mass is very, very large compared to the typical temperature of your fluid, then it's actually possible to, like, you take some Taylor expansion, and then you show that when you're building the quadrature, like your weighting function that you use to construct the method expanded at the second order is basically the same weighting function that's used to build the classical lattice Boltzmann method. So in that sense, there is a convergence between the two. And then there's a second one, which is probably more interesting and important, and gives me also the opportunity to say something that I forgot to mention during the presentation. And that is, I forgot because I actually skipped it. And that is, so we have this other setup. This is a setup where we have like a graphene sheet where there is an injector and an extractor of current, and this type of geometry is placed on the same side of this sample. And this geometry was used to expose the hydrodynamic behavior of electronic transport in graphene by observing the fact that there are these anomalous voltage drops nearby the current injector, which is then justified by the possible presence of this current circulation near the inlet. So basically, this was a way also to benchmark our scheme and to make sure that we were doing the things correctly, in particular for what concerned converting from physics to lattice units. That was not like trivial here. So for this specific setup, these people also developed some semi-analytic solution for what should be the value of the electrochemical potential nearby the injector of the current. And in this figure, I'm showing you that we are reproducing the benchmark. The thing is that here, like, and in general in actual experiment, like the typical values of the current that you can inject in these samples without burning them makes so that the velocity is very, very low compared to the Fermi velocity. So we cannot talk about relativistic flow. So at the end of the day, if you do the same simulation with a classic lattice Boltzmann method here, you get exactly the same result. And actually, based on this observation, like to work out this particular figure where we have explored a very wide range of parameters, and I had to perform already a lot of simulation. So because of the observation that the classic lattice Boltzmann was doing as much good as the relativistic one, and that the classic one was times, obviously, less expensive from a computational point of view, here we basically use the classic lattice Boltzmann method. So thank you for your question. That gave me the possibility to say that.
Thank you very much. So is there any other question from the audience? Maybe I have one quick question, Alessandro, regarding the computational complexity. If you can mention, you already mentioned something during the presentation, but I mean, some more technical details on how much expensive is this relativistic Lattice-Boltzmann method if compared, let's say, to the classical Lattice-Boltzmann methods of the past. Can you give some comments?
So I have here an extra slide where I've shown you a couple of computational figures. Obviously, when you work with, like, there's some complication are due to the fact that you have just more velocity. So more velocity means that the algorithm is more costly. But then inside this algorithm, there is like a lot more. There are like evaluation of Bessel coefficient, iterative methods to solve for the equation of state, in case you are not using simple equation of state. And plus, you have also an eigenvalue solver for calculating the energy from the energy momentum tensor. So all in all, it's a lot more of floating point operation, but this has the positive effect that is so costly that like we are not anymore bounded by memory accesses. And when you work, for example, on a GPU where you have like really a lot of floating point power there, then you can extract very large peaks of performance. And at the end of the day, this is, say, roughly speaking, about 10 times slower than a classic Lattice-Boltzmann method, which might seem a lot, but still it's a lot better than Monte Carlo approaches that are used in this field.
Okay. Good. Thank you very much. Is there any other question from the audience? If that is not the case, I would like to thank Alessandro once more for this really inspiring overview lecture. And we go for the lunch break, and we start back again at 2:20 with another plenary lecture by Luciano Rezzolla. Thank you very much to all the speakers of this session. Thank you very much to all you that attended the session. Catch you later.